Hey guys! In this video we're going to cover the last aspect about electronegativity that you need to know. This is super duper important, so pay close attention and feel free to rewind or rewatch any part of this video. You've probably heard the phrase opposites attract. That phrase also applies here. Protons and electrons are attracted to each other because of their opposite charges. The strength of that attraction depends on the number of protons in the nucleus. So think of the nucleus as the sun of the atom, and just as the sun controls all the planet's orbits, the nucleus is the one controlling the orbits of the electrons and doesn't just let them float away from the atom, right? Now get this, there are two things that we need to know. One, the force coming from the nucleus increases with more protons. Makes sense, right? The more protons you have, the more of a positive charge you're going to have coming from the nucleus. The higher the charge, the stronger the force. Iodine here has 53 protons, so that's a plus 53 charge. So that nucleus is super strong and is really going to pull those electrons towards itself. 2. As we know, electrons feel the force that the nucleus has, and electrons stay in orbit because of that. But all of the electrons do not feel that force equally. Rather, the closer you are to the nucleus, the more you will experience that force. You're going to feel a stronger force because you're literally closer. And those that are further away from the nucleus, say in this last shell over here, are going to feel it much, much weaker. And we can go back to our example of the solar system for this. Let's take a look. The sun exerts the same force on all of the planets, but the planets feel that force differently based on how far they are away from the sun. For example, the Earth here is much closer to the sun than Pluto, and consequently, the force that the Earth experiences from the sun is 15 times larger than the force that Pluto feels. Let's go back to iodine. As you can see, all of the electron shells except the valence shell are fully filled to capacity with electrons. Why? Well, electron shells are actually energy levels, and all of the electrons in the same shell or energy level experience the force from the nucleus the same because their distance from the nucleus is the same. So let's take a look at this first energy level right here. It has two electrons, one here and one here. As we can see, the distance from each electron to the nucleus is exactly the same, right, because it's a circle. And so the strength of the force that these electrons are going to feel from the nucleus is identical. All right, so another thing that we need to know is that energy levels increase as you move away from the nucleus. So this is the first energy level, the second, the third, the fourth, the fifth, and etc. Atoms really want their lower energy levels to be super stable by having a full shell of electrons because the electron shells closer to the nucleus, aka low energy levels, experience the force coming from the nucleus a lot more and a lot more strongly than electron shells further away. So let's take a guess. Pick an electron that experiences the force coming from the nucleus really intensely in iodine. If you chose an electron in either the first shell or the second, you would be correct. But how does this all relate to electronegativity? Well, we know that electronegativity means how much an atom wants to gain an electron. But what if we compare atoms that have the same number of valence electrons, like fluorine and iodine? As we can see, fluorine's valence shell over here is only one shell away from the nucleus. Its valence shell is the second energy level, so that electrons in this valence shell can really feel the pull of the protons in the nucleus. It's like this atom is super aware that something is missing. So fluorine still really wants to gain an electron. Let's take a look at iodine. See how many shells iodine has? That's super insane. So all of these electrons in the middle here are repelling the valence electrons. That means they're pushing the outer electrons away from the nucleus. And so those electrons don't really feel the pull in the nucleus because they're so far away. We call this shielding. All of these inner electrons are literally shielding the valence electrons from the force of the protons coming from the nucleus. Because of that, the nucleus isn't as hyper-aware that it's missing an electron. Of course, iodine still wants to gain an electron because it has 7, and therefore we know that electronegativity increases with the more valence electrons that we have, but it doesn't want into the same burning desire that fluorine does. So, iodine is less electronegative than fluorine because iodine has more shielding. Let's practice.